Alright, you're gonna have to bear with me because I am tech illiterate. I was not able to live stream this video, and well, I guess that's all she wrote. So let's start off by giving a review of materials that we have already covered so far. So first of all, we've got resistors, which resistors, what they do is they convert electric energy, which voltage, current, into heat and light, something that removes the energy from the system. Capacitors, they convert electric energy into electric field energy, which is stored between two electrically charged plates, and inductors, which the inductors take the electric energy and convert it into magnetic energy as currents passing through coils surrounding some kind of a metal core. So we have these three elements. Previously what we did was we took these three elements and we put them into a circuit like this. We applied a constant voltage and we just waited to see what happened. Usually the result of each one of these was they showed either an exponential growth or an exponential decay function. The voltage of all three of these sum to the voltage source. So this is kind of just a basic review of what we've covered so far this semester. Now, one thing that changes the entire game here is if instead of using a DC source, we use an AC source. What is the difference between a DC source and an AC source? Well, in a DC source, the voltage supplied per time is constant. Whereas in an AC source, the voltage applied per time is a sinusoidally oscillating function. So before we really get started on how we can analyze this circuit with a sinusoidally oscillating power supply, why don't we discuss a little bit about what is a sinusoid and what does that mean? So to begin, if we have a sine curve, looks something like this. That sine curve has, let's assume that I can draw this symmetrically. That sine curve has this, which is the amplitude, which is the same on both sides, amplitude. And all that is the difference away from the center line that the peak goes. And then you have a period. Here the period is what is the distance on the time scale between when this curve repeats itself again. So here, the distance here is, this is known as the period. And we give the period by t. And then we can do some calculations based on that. The period t is equal to 2 pi over the frequency. Oh, I guess that, no, this is, my apologies. This is 1 over the frequency. Omega, which is the, it is referred to as the angular frequency, is equal to 2 pi f, or that's equal to 2 pi over t. So what we have here is the equation that is generated from this is, if we call the amplitude, we'll call that f. Our sinusoidally oscillating circuit, we'll call that V AC, is equal to F sine omega t, and we're going to add a phi. Now what is that phi? Well, imagine instead of this, where the sinusoid begins at 0, imagine we had a sinusoid that began like this. So here the period is the same. We still have the same distance on the time scale between where it starts and where it stops, but it starts at a different voltage. When we assign time 0, phi means, well, we've shifted this over about this far. So here phi may be negative 15, negative 20, negative 30 degrees. What this phi does is this is called a phase shift. Okay, so this is angular frequency. This is basically the higher number that this is, the faster you see this oscillate. The more peaks you see in the same amount of time, the more scrunched it is. So if we increase omega, this entire thing gets scrunched up to the left. If we decrease omega, this stretches out to the right. Here, F, this is our amplitude. If we increase F, we see the graph grows this direction. We decrease F, the graph actually shrinks. So we have all of these variables now. We've identified phi. Let's go ahead and start with a very simple circuit. Okay, we'll start with just this. Now this is an AC source applied to a capacitor. Okay, so we know VAC, let's say it's equal to the amount of power that comes out of a power plug. It's equal to 110 volts times sine of omega t, where here the frequency is 60 hertz. So that means omega is equal to 2 pi times 60. Pardon the fact that I can't do this in my head. So that is 377 degrees per second. Okay, well I guess that might be radians per second, but, not degrees. Okay, so this is our function, this is what we have. We know that if we were to do KVL across the circuit, KVL says, well, the sum of the voltages in a loop equals 0. So if we add all of the voltages in the loop, we only have a voltage here and we only have a voltage here. So the voltage here must equal the voltage here. It says that VAC is equal to VC, which means they're both equal to 110 sine 377t. Okay. There was no math involved in that. But the thing that we need to consider now is, let's say we're trying to figure out the current through this capacitor. What is IC? Well, we know that the current through the capacitor is given by IC is equal to C dVc dt. So if we give C as 1 microfarad, then IC is equal to 1 times 10 to the negative 6th times dVc dt, which is the derivative of this. d dt of 110 sine omega t, which omega is 377. If we take the derivative of this, we get 1 times 10 to the negative 6th times, well, this is omega times 110 cosine omega t. Okay, that's all the derivative is. So we just took the derivative of this function, moved it down. Here's the derivative. We know that w is equal, omega is equal to 377. So, again, pardon me because I can't do this in my head. 377 times 110 means that this is 1 times 10 to the negative 6th times 41 470 times cosine omega t. Okay, well, times 10 to the negative 6th. Let's see if I can use my calculator correctly. I'm sure this is why you tuned in to watch this lecture, was just to see me use a calculator on my phone poorly. I know that's why I watch. I will rewatch this just so that I can improve my self-loathing here. I do not know how to... Oh, there it is. Negative 6. Or I could have just moved the decimal place over 6 places. It's Tuesday. Bear with me. 0.04147 cosine omega t. And this is amps. Okay. Now what we're going to do here is, what is the difference between our VAC, which is also our VC, and our current coming out of here? Well, this is not, if we were to plot the voltage looks like this. Okay, so this is VC versus time. Here our period is 1/60th of a second. Here our amplitude is 110 volts. Goes down to negative 110 volts. That's our voltage. If we were to plot our current looks like this. It's a cosine function. And if I try to get... Guess I'm not the world's greatest artist. Thank goodness this is an art class. Okay, it looks like this. It has the same period. This here is 1/60th of a second. This is IC. Okay, and the amplitude here is 0.04147 amps. But it's moved. It's as if we took this function and moved it this way. That is the function of when we identified phi, that phase shift angle. That's the function of it. We can actually rewrite this function as, instead of a cosine function, this is a sine function that has been shifted 90 degrees left. So we can rewrite this as 0.04147 sine omega t plus 90 degrees. So if omega is in radians per second, we're going to put it in degrees so that we can add 90 degrees to this. IC, which is the current in our capacitor, is phase shifted 90 degrees from this. What does that mean? Well, it means that if we apply a voltage, we're going to see the current show up 90 degrees ahead of where this is. It'll be 90 degrees, it's like future vision here. What this is called the current leading the voltage. Current leads the voltage. It means this happens before this happens. So if we just look at this part of the voltage spectrum, which is the identical piece of this, on the time scale this happens at 0. On the time scale this happens a little after 0, 90 degrees after 0. A whole 1/4 of the way through a sinusoid cycle. So this is just a little bit of terminology here. What we're dealing with is a phase shift. The current is going to occur before the voltage is applied to it. Before we see this, and this is only true for constant normative oscillating voltage sources. Okay? That's what we see. So this is for a capacitor. Now, let's say instead of for a capacitor, we're going to be doing this with an inductor. So I'm going to take this, I'm just going to replace it. Now let's start with a resistor. And we'll say that R equals 1000 ohms. Okay? Now we're going to apply VAC is equal to 110 sine omega t, where omega is once again our 377 degrees per second angular velocity. Okay? Alright, so that happened. Now what? Well, we've got omega given here. We know that VR, which is the voltage across our resistor, is equal to our VAC. Why? Because KVL, again, applies. The voltage in a loop has to be equal to 0. So we know that this voltage is equal to this voltage. The amount of power supplied has to be equal to the amount of power dissipated. So we know that this is also equal to 100 sine omega t. Okay, what's the current in here? Well, here we use Ohm's law. Okay, Ohm's law states that the current through a resistor is equal to the voltage through a resistor divided by the resistance. So we've got the voltage here, 110 sine omega t divided by 1000. Now I'm not going to pull out my calculator this time. And that's what you were waiting for. I know I tend to do that. So this is 0.110 sine omega t. Now if we were to plot the current through the resistor versus the voltage in the resistor, here, this is VR versus T. We're going to have our nice sinusoid. Okay, and our IR versus T is the same. Now here the amplitude is, this is 110 volts. Here the amplitude is 0.110 amps. So not quite the same amplitude, but it has the exact same shape. They both start at 0 at the same time. They both travel basically in the same pattern. They're both harmonic with each other. They oscillate at the same time. They both reach 0 at the same time. So if we're looking at this, if we're going to rewrite this equation as F sine omega t plus phi, what is our phi value here? Well, it's 0. We don't have, this is a sine omega t, this is a sine omega t. There is no phase shift between them. So what we say is that for resistors, current is going to be in sync with the voltage. Not Backstreet Boys. In sync. Remember that. Okay? we've got the current in sync. They're both going to occur at the same time. Well, we've known this whole semester that through a resistor, whatever the voltage is whatever the current is. If we can find the current that's traveling through the resistor, we can easily just multiply it by the resistance and find what the voltage is through that same resistor. So we've known that. This is nothing shocking to us. But in the terms of AC sources, it's just a new way of looking at it. So now let's go ahead and look at what is an inductor. So here, I'm just going to replace this with an inductor. Okay, and we'll say L equals 1 Henry. Okay, again, we're applying the same voltage source. Again, Kirchhoff's voltage law is true. We know that the amount of power generated by the power source is the amount of power that is consumed by this source. So we've got VL is equal to VAC is equal to 110 sine omega t. Okay, there's no other voltage being dissipated in the entire circuit, all entirely going through this inductor. Okay, what is the current going through the inductor? Well, we know that the relationship between voltage and current for an inductor is that VL is equal to L DIL dt. So if we rearrange this, we get IL is equal to 1 over L times the integral of IL dt. I wrote IL twice. That's VL. Okay, we know that this relationship stays true. With this relationship being true, and this relationship being true, and since we already know voltage, we just have to take the integral of this to find the current. So we'll take the integral of 110 sine, so IL is equal to 1 over, well, it's 1, times the integral of 110 sine omega t dt. Which that is equal to, the integral of this is 110 over omega times negative cosine, because the integral of sine is a negative cosine, omega t. Okay, which this is 110 divided by 377. Now we do actually need my calculator for this one. As we get 0, this is a negative 0.2918 cosine omega t. Okay, once again, cosine omega t, well, okay, let's plot this real quick before I get ahead of myself. So we've got VL, and we've got IL, we've got our voltage source that we're applying over time. Here the current is given by a negative cosine function, so it starts down here. This, like that. Okay? Once again, this is not art class, and I promise you I can draw straight lines. Just we'll blame it on the fact that I am insufficiently dosed with caffeine this morning. Okay, our amplitude here is, this is 0.2918 amps. The amplitude down here, again, this is 0.2918 amps. This is a negative 0.2918. This is a positive 0.2918. Has the same exact periodicity, has the same period, has the same frequency, has the same angular. I mean, we're still using omega here. We haven't changed what omega is. They're all operating off of the same speed cycle, but this is almost as if it has been shifted this far, 3/4 of the way through the sine curve. We're looking at a phase shift of about 270 degrees or negative 90 degrees. Those are both the same thing. Okay, so it's almost as if we were to continue this backward, we're starting here, and we're just moving this graph this direction. So this point corresponds with this point corresponds with this point corresponds with this point. Well, what we've done is we've shifted this curve is moved backwards from this. So if we were to write this as our standard sign notation, IL is equal to negative 0.2918 cosine omega t. Well, we could rewrite that using our phase shift, using our phi value. We can rewrite this as 0.2918 sine. Now notice the negative sign goes away. Why is that? Well, it's because a negative cosine is just a cosine 180 degrees phase shifted. 0.2918 sine omega t minus 90 degrees. Okay? These are the same things. A cosine function is a sine function minus 90 degrees. Cosine function, sine function minus 90 degrees. A negative cosine function is. A positive cosine function is a sine plus 90 degrees. So what we'll say for an inductor, because we have this negative phase angle, the current lags the voltage. Okay, the voltage has to occur in order for the current to flow. Voltage has to come first. In a capacitor, it's the other way around. The current leads the voltage. The current has to precede the voltage. Whereas in an inductor, the voltage has to precede the current. We will see that rise in voltage before we will see the rise in the current. Because of that derivative, that integral relationship here. So, inductor, current lags the voltage. Capacitor, the current leads the voltage. And for a resistor, the current is in sync with the voltage. All things that we've already known, we just haven't applied them to an AC voltage source yet. So, this is where things get a little bit funky. If we were to, instead of just only having an inductor in the circuit, let's say we were to have an inductor and a resistor. If I were to take this out, I'm just going to erase everything but my voltage source, and I were to put a resistor and an inductor in, L and R. Well,